Hello, my name's James Kermode and I'm an academic in engineering at Warwick. In this short video I'm going to tell you a little bit about my research, which is in the field of computational materials engineering in my research group in the Warwick Centre for Predictive Modelling within the School of Engineering at Warwick. In particular, I'm focused on describing materials right down at the atomic scale, so looking at individual atoms and bonds and trying to use that to understand how materials break through a process called fracture. There are a number of different example systems that I've worked on, and the thing that they have in common is a combination of chemistry, so breaking of chemical bonds right down at the atomic scale, looking at individual bonds breaking apart, and mechanics, so chemomechanics together. And mechanics means the application of forces or stresses far away from where the material is actually breaking up. So if you think about a typical thing breaking, the forces are applied far away and their load is concentrated right down on a tiny microscopic region where chemistry happens and bonds break. A few examples that we'll look at in this brief presentation include fracture of drill bits that are used, made out of diamond and used to make extremely sharp cutting tools. Friction is closely related to fracture, so rubbing a tiny this is a tip of an electron microscope rubbing on a surface and trying to measure the roughness of the atomic scale surface underneath. And then moving up to larger scales, we might be interested in trying to understand how to break up rocks out of the ground when they've been dug up in a mine without having to put too much energy in. So reducing the energy cost of mining by trying to understand the underlying fundamental processes that are involved in breaking materials down. Rocks actually have a lot in common with materials such as glasses. The structure is very similar, and glasses are a bit easier to look at in the laboratory. So the sort of most obvious example of what's called a very brittle material is glass. We'll look at that a little bit more in a minute. More recently, I've also been looking at metallic systems, so trying to understand things like superalloy turbine blades that are found in jet engines. So there's a picture of that up on the top right here. This is a turbine blade within an aircraft engine. It's actually made out of a single crystal of materials. So inside the turbine blade, it's grown in a mold. All the atoms are lined up perfectly in a perfect crystalline lattice. And that means that it's really important to understand the processes right down at that atomic scale to be able to design and improve future generations of alloys. The last example down at the bottom right is future materials for making fusion reactors, or in particular for shielding the outside of the fusion reactor. The material that's used for this is tungsten. It's the only thing that can cope with the massive amounts of heat that a nuclear fusion reactor puts out, but we have to understand better how to make it strong enough to last for a very long time in those very challenging radioactive conditions. So let's look a bit more at what's going on when something breaks. This is what I found when I came into my office a few weeks ago. A massive crack through the glass wall. You can see that it's really broken up into tiny pieces. If you zoom in on those individual cracks, then what you'll find is that they're really sharp, and you can actually zoom in right down to the atomic scale. So this picture on the bottom left is an atomic force microscope image. It's not actually an image of my door, but it's of a similar piece of glass, and it's down at the 500 nanometer scale. So that's half a micron in scale, and you can see that the crack shown in green inside is really sharp, right down at the atomic scale. In my case, I think the problem that had gone wrong was there were some residual stresses left in this big window after it had been installed. So it wasn't quite straight, and there was a stress there that eventually became critical, and then cracks just exploded throughout the material. We'd like to understand how that can happen, what might cause it, and how it could be prevented in future. The other example, the other kind of fracture that I'm interested in is called ductile fracture. So that's what typically occurs in metals, where you pull on a piece of metal and it gets thinner in the middle and then eventually separates into two pieces. If you zoom in on what's going on inside a ductile fracture, you find it's quite different to the very sharp brittle case that we see in glass. Instead, there are lots of little holes called voids that grow inside the material, and eventually enough of those holes combine and make a critical size void, which causes the material to fail. So it's quite a different process. So far, most of the modelling I've been doing in my research group is focused on the brittle side of things, on the side where it's very, very sharp, because it's easier to describe what's going on there with atoms. Another kind of material defect that we might be interested in is called a dislocation, and that is like a mistake in the layout of the atoms that make up a crystal. There are two different types, edge dislocations and screw dislocations. In an edge dislocation, you can think about there being an extra row of atoms that shouldn't be there. So on the left-hand side, you can see with the solid black line an extra row of atoms in this crystal that cause a mistake in how it's laid out. The other type of dislocation is a little bit harder to visualize. That's called a screw dislocation, and that's where the shift is instead in the other direction, in the out of plane direction, and the atoms instead have a mismatch in that they've been pushed backwards on one layer. If we look in real materials, we can find very close analogies or very good pictures. This is a microscopic image of what an edge dislocation really looks like, and you can actually resolve the individual atoms. This is a transmission electron microscopy image, TEM image, and you can really see the atoms that form this dislocation. You also find them in more realistic examples in things like brick walls. So if you look at this wall here, you can see that there's a mismatch in the layers of bricks and they don't line up properly. So on the right there are two rows that become just one row on the left. You can also find them in the natural world, things like cactuses. So this cactus here you can see has got an edge dislocation in it. In the top half there's an extra row of spikes compared to the bottom half. So these are all the kinds of phenomena that occur on all different scales, but in my research group we focus on trying to understand them right down at the bottom, right down at the nanoscale. And we use a range of different modelling techniques to do that. I'm going to give you just a couple of quick examples of the kinds of things that we might be interested in doing. So one way to model things is to use balls and sticks to represent the atoms. That's quite useful, but not very accurate. We can model maybe 1 million atoms in that way and get a description of what's going on. So for example, we might be interested in looking at these dislocations that I was talking about inside a jet engine turbine blade. So this is a simulation of the inside of one of those superalloys, where we might be interested in trying to understand how dislocations move around. So let me just play the movie again. Dislocations move around inside parts of the material. Here we've got a separation into two different types. It's a bit like bricks and mortar that make up a wall. The superalloy is made up of a gamma phase, shown on the left-hand side, where my dislocation is moving around, and a harder gamma prime phase which has got extra aluminium in it and is tougher, and the dislocations can't get inside that part. And we'd like to understand why that is and improve the properties of the material and improve the accuracy of the modelling as well. In terms of fracture, we'd like to understand how cracks propagate. So we know from experiments that the cracks should be completely sharp, like in the picture on the left. But if we run a simulation just using one of these simple interatomic ball and stick models, we don't get a very good description. We see that instead of being completely sharp, this crack gets a bit blunt and gets messy. We see all of this nasty triangles and other shapes of atoms around here that we'd prefer not to see. This isn't a good model of what's going on in reality. And in that case, we have to go up to another level of accuracy. We have to use something called density functional theory, which is a model where we include not just the atoms as balls and sticks, but electrons as well. So thinking about how the electrons stick the atoms together. We can use that on its own, and it's quite useful for predicting how hard you have to pull to break something. So this is a piece of silicon carbide. We did some calculations where we looked at how hard you have to pull for it to break, and then some colleagues at Imperial College in London did experiments and found a really good alignment between the measurement they made of the fracture energy, how hard you have to pull to break it, and then the calculations that we did using this quantum mechanical DFT simulation. But it's not always possible to separate things out like that and to do a big simulation for not very accurate situation, or a small but very expensive and very accurate simulation. Sometimes we need to put the two together, and that's something I've specialized on in my research group. So we've worked on, for example, sticking together a quantum mechanical description of a system shown here with the blue atoms centered on a cracked tip, combined with a classical description of the rest of the system where not so much interesting is going on. And that's been very useful for describing complicated systems where we might have lots of things happening at once. So this is a good example. Here I've got a crack tip that is running around and being driven towards a dislocation. So I've got both types of defect in this material, a crack and a dislocation. And what we see actually is that the crack gets pulled down towards the dislocation core, and then eventually it annihilates the core, it makes it go away, and then takes a diversion up the stacking fault, which is a weak plane, weak interface in the material. So here we're using the computer to really predict what we would expect to see in reality if we were able to zoom in this far and take pictures very quickly. The last example I want to show you is what happens if you put water or oxygen, if you put molecules into the situation. They can actually react and perform chemical reactions which can break bonds when otherwise you wouldn't be pulling hard enough to do so. This is called stress corrosion, and it's what happens perhaps in the glassy door that I showed you at the beginning. So in this case we've got a molecule of oxygen that's coming in, let's just see that again, and causing bonds to break when otherwise we wouldn't be pulling hard enough for them to do so. This makes cracks propagate very, very slowly because we have to wait for another molecule to get there before the next bond breaks. Okay, that's pretty much all we've got time for. So I want to finish up with a few takeaway points, but first, take care not to forget to thank all of the financial supporters of the research that I've described to you, which includes UK funding agency, the EPSRC, the Royal Society, the Leverhulme Trust, European Commission, and also very large-scale computing facilities that are needed to carry out the kinds of simulations that you've seen in this brief video. So Archer is the UK national computer facility. Actually, it's just being replaced by a new machine called Archer 2, and I've also had computer time at the US and from the European Union under the PRACE initiative. So what are the main messages I'd like you to take away from this brief masterclass? First of all, an understanding that the way things break or fail in other ways is dominated by what happens at very tiny nanoscopic scales, so intrinsically involves separating atomic bonds, which means we need to understand the chemistry of atomic bonding, and that's controlled by the electrons which sit between atoms and bond them together in a covalent material or in a metal, which are delocalized throughout the entire metal and control bonding in that way. I want to hopefully convince you that computer modelling is really important for describing these processes. It's very hard to do experiments right inside something that's breaking, very complicated and expensive to do in situ experiments, and so modelling plays a very important role in our understanding of these kinds of processes so that we can in future reduce the impact of things breaking in unexpected ways, design materials to be stronger and longer lasting, and also to allow us to make use of new materials as they're discovered. If you want to get into this kind of area of research, there's lots of different ways of doing it. So the research that I've described fuses knowledge and expertise from many different undergraduate degrees, in particular physics, chemistry, engineering, materials science, and even some mathematics as well. The algorithms that we use to carry out our simulations benefit a lot from insight from applied mathematicians. So any of these undergraduate degrees would be a great way to get into this field of study if you're interested. Do take the opportunity to find out more about the topics that we've discussed. Wikipedia is a great starting point, especially if you follow it up with some of the linked articles and references, but researchers like me make great use of Wikipedia, so don't feel like it's not an appropriate place to research. But you can also discuss it with your teachers or with your family, and I'm sure there'll be lots of interesting conversations that you can have after all of the interesting videos you'll see as part of this masterclass.
Haia, croeso i'r sesiwn yma ar fywyd fel myfyriwr Peirianneg neu Ffiseg. Thomas dwi, na i arwain y sesiwn. Dwi'n astudio Peirianneg Mhrifysgol Caergrawnt. Dwi yn blwyddyn olaf iwan, sef blwyddyn 4 yng Ngholeg Queens. Ac es i'r ysgol yn Mangor yn ysgol Turbine, lle nes i studio maths bellach, cemeg, ffiseg a'r bac ar gyfer lefel A. A werth deud, tan diwedd blwyddyn 12, do'n i'n yn sicr ben i am fynd i geisio i studio yn y brifysgol. O'n i'n ystyried lot o'r kind of pynciau yn y maes, gwyddoniaeth a maths. Peirianneg nes i ddewis yn diwedd, ond nes i ddewis cwrs cyffredinol. So hynny ydy dim mechanical engineering neu civil engineering, SEM engineering, chos do'n i'n hollol siŵr be'n union o'n eisiau ddeud. O'n i jyst yn gwybod ni fe rhyw diddordeb yn cynaledwyedd, egniad newyddadwy a falle. A na i roi syniad i chi heddiw o just fatha be mae bywyd fel yn astudio'r pynciau yma. So, yn kind of eang, y kind of pynciau dyn ni'n ystyried ydy Peirianneg a gwyddorau ffisegol, hynny dyn, physical natural sciences. A mae'na rhai prifysgolion lle, literally dyma'r cyrsiau ydych chi yn geisio amdano fo. Maen nhw'n cychwyn yn hollol eang a gyda bob un blwyddyn, ydych chi'n mynd yn mwy manwl. Wedi deud hynna, mae'na rhai prifysgolion lle ydych chi'n mynd ag astudio, allan rhan fwyaf, actually, mechanical engineering neu civil engineering, aeronautical engineering o blaen, a hefyd fydda Ffiseg neu allan astronomy, ie, na fo, yn sydd bin. Be bynnag sy'n siwtio chi, os ydych chi'n hollol siŵr ar beth ydych chi eisiau gwneud, ewch am rei manwl, ond dwi yn hapus iawn esu am cwrs mwy cyffredinol. Dwi ddim yn teimlo fel dwi wedi colli allan ar fanylder yn y cwrs yma. Dwi jyst yn teimlo fel dwi wedi cael addysg hollol eang, a mae'n edrych bod yn rhy handi fi, especially achos dwi'n hollol siŵr beth dwi eisiau mynd i wneud. So 100% recommend. Dwi heb sôn am maths. Mae maths yn y brifysgol yn eitha gwahanol i'r ysgol. O beth dwi'n weld, mae lot mwy am fatha yr ochr profi theorems, meddwl am bethau, sy'n chwythu meddwl fi, fourth dimension y falle. Mae maths yn holl bwysig i Ffiseg a Peirianneg, ond mae lot mwy fatha dilyn ymlaen o'r ysgol. Defnyddio maths ydych chi, dim just gwneud maths gwerth gwneud maths. Ond os ydych chi'n licio'r theorems falle, ystyriwch maths. So, i roi rhyw fath o syniad i chi o fatha modules sy'ch chi'n gymryd i arholiad yn y brifysgol, jyst chydig o esiamplau o flwyddyn cyntaf i gyntaf. So, blwyddyn 1, gen i fi papur maths, papur electromagnetism a fatha trydan, essentially. Structures and materials, a mechanics a thermofluids. So, hollol eang, da chi'n cyfro bob math o bethau, ond fatha, y sgiliau a'r dulliau maen nhw'n ystyried yn eitha sylfaenol ar gyfer gweddill y cwrs. Fast forward wedyn i'r 4edd flwyddyn, a dwi'n gwneud y modules hynod fatha arbyn, specialised. Dwi'n cael fatha dewis yr hei dwi eisiau gwneud. Gyda fi yn fatha egniad newyddadwy, sustainable water management, fission and fusion systems. Maen nhw'n really specific. A trwy'r cwrs, yn enwedig yn y blynyddoedd cyntaf, mae'n hefyd fatha gwaith mwy ymarferol, sgiliau ymarferol fel rhaglennu, gwaith lab, sifil arfer, fatha dilyn y papurau a'r arholiadau, a hefyd sgiliau dylunio yn Peirianneg. A mae gen i fi prosiect wedyn hefyd yn y 4edd flwyddyn sydd lot mwy fatha gwaith annibynnol i fi. Dwi'n gwneud rhywbeth hollol specific, a mae hwnna debyg iawn i maths a Ffiseg hefyd. So, cychwyn hollol eang. Hyd yn oed os ydych chi'n mynd am fatha Ffiseg neu Peirianneg specific, fydd o'n hollol eang, fyddwch chi'n gwneud lot o overlaps efo fatha y gwyddorau a'r Peirianneg, y pynciau Peirianneg eraill. A mond wedyn allan y 4edd flwyddyn neu'r 3edd flwyddyn, fyddwch chi'n gwneud rhywbeth fatha really, really specific a fi hollol fatha cael gwaharad ar pethau ydych chi ddim o'r eidrwydd yn mwynhau gwneud. Ond be di fatha studio fatha fel, beth ydych chi'n gwneud, ydy ddim yr ysgol. Darlithoedd, fel arfer, dyma sut ydych chi'n dysgu, fyddwch chi'n cael fatha nodiadau, fyddwch chi'n gorfod gwneud eich hunan, ond allan fatha anodi nodiadau sy'n dilyn fatha manyleb eitha fixed. A fyddwch chi'n cael fatha problem sheets i fynd efo'r darlithoedd yma, fyddwch chi'n gwneud nhw allan wedyn seminar neu'n achos fi yng Nghaergrawnt supervisions neu tutorials a falle i fatha mynd trwy'r problem sheets. Os gennych chi broblem, os gennych chi gwestiwn, allan mestyn dealltwriaeth chi'n bellach. A wedyn weithio mewn fatha lab sessions sy'n fatha cysylltiedig efo'r modules penodol. A wedyn ar yr ochr allan fynd fatha chydig o waith cwrs lab neu rhaglennu nhw fath ar yr ochr, ond fel arfer yn enwedig blwyddyn cyntaf, jyst arholiadau ydy o'i gyd. yn y bedwaredd flwyddyn dwi'n edrych fyny yn gwneud chydig o draethodau, mae hwnna jyst yn digwydd bod dyna di'r dill maen nhw'n asesu'r modules dwi'n mwynhau gwneud. O ran amserlen, mae gyda fo strwythyr, gyda'r pynciau Ffiseg a gyda'r pynciau Peirianneg. Mae'r diliaethoedd, da chi angen mynd iddyn nhw, mae gennych chi fatha manyleb sydd wedi setio, gennych chi labs hefyd. Mlwyddyn cyntaf fi ar ail flwyddyn, o'n i essentially yn yr ysgol Peirianneg 9 glot o bore tan 1 o pnawn, wedyn cinio. A wedyn ta'r pnawn fwy fyny i fi, weithio sy'n mynd i gwneud gwaith, ond weithio sy'n mynd i gwneud beth arall, weithio ar y penwythnos wedyn, ac wneud gweithio yn y nos. Ond dal yn eitha fatha, ddim 9 to 5, blaen fatha chydig wythnosau bob hyn a hyn efo project work. Dio mor llawn a hynna, ond gennych chi fwy o strwythyr na unrhyw bwnc arall. Fyswn i'n dweud, os ydych chi'n mynd ag astudio Peirianneg neu Ffiseg. Arholiadau fel dwi wedi dweud ydy'r ffordd o asesu fel arfer, ond edrychwch ar y cwrs specifics da chi'n ystyried os mae hynna'n rhywbeth da chi'n poeni am. O ran fatha tips ar gyfer ceisio i'r pynciau yma, fyswn i'n dweud bod sgiliau rhaglennu yn holl bwysig, a fyswn i yn hollol argymell i chi ddysgu ychydig o raglennu os ydych heb yn barod. Do'n i heb tan i fi gyrraedd yn brifysgol, ond dwi'n sbio nôl, dyna'r un peth fyswn i'n deitha fatha fi pan o'n i'n ifanc, dysgu rhaglennu. Mae yna iaith yn enw Python, dyna maen nhw'n ddysgu yn flwyddyn cyntaf yn rhan fwyaf o brifysgolion, rhan fwyaf o maths a Ffiseg. Yn rhan fwyaf o Peirianneg. Mae o'n ffyn, a dwi'n difaru peidio fatha bod yn well yn efo pan nes i gychwyn, so fe gwneud bywyd fi'n haws. A mae'n rhywbeth rili da i roi ar fatha cais, especially os da chi'n defnyddio Peirianneg i rhedeg rhyw fath o sensors neu project neu robots neu fath. Ffantastig. Hefyd just unrhyw fath o ysgol haf, darlith, masterclass, cystadleuaeth, just cymrwch pob un cyfle, achos maen nhw'n gold mines ar gyfer just ehangu dealltwriaeth chi, gwella'ch ceisiadau chi, a just testio'ch hun, ydw i'n mwynhau hyn, achos os da chi ddim, allai dim dyma'r cwrs i chi. A maths. Os da chi'n ofyn maths, mae yna maths, mae yna lot o maths. Mae rhaid i chi fod yn gyfforddus efo maths. So, maths. Ac os da chi'n gwneud ymchwiliad unigol yn bac, no-brainer, gnewch ar rhywbeth sy'n gysylltiedig efo'r pwnc. Diolch yn bod yn fatha hollol mathematical na'n byd, ond enghraifft i fi, mae yna lot o ochr cymdeithasol a allwch chi ar gyfer egniad rhyw ddadwy, fyddwch chi'n gallu sgwneud traethau ar ddim just calculations. A wedyn, jyst yn meddwl am gyrfaoedd ar y diwedd, wel, yn amlwg, os da chi eisiau mynd a bod yn peiriannwr neu ffisegydd neu gwyddonwr, dyma'r pynciau cywir i fod yn gwneud, fel sa'ch chi'n disgwyl. Ond hefyd, newch chi ffeindio bod lot o pobl sy'n studio Peirianneg a maths a Ffiseg ddim o reidrwydd eisiau mynd a gwneud rhywbeth hollol gysylltiedig fe'r pwnc na, ond maen nhw'n mwynhau'r pwnc, maen nhw'n gweld bod o'n dysgu sgiliau buddiol iawn i chi, sydyn mae pobl sy'n licio heirio. Mae lot o bobl yn licio heirio graddedigion Ffiseg a Peirianneg, yn enwedig yn y finance sectors, consulting sectors, a lle mae lot o arian, ond hefyd mae'n gennych chi bobl fel fi sydd ddim eisiau mynd a gwneud gwaith arian, ond sicr ddim eisiau gwneud gwaith mwy hands-on Peirianneg chwaith, dwi lot mwy o berson. Alla llai ymarferol, ond mae hynna'n ffain, mae Peirianneg yn y brifysgol yn bennaf yn academaidd, ac mae angen rhyw fath o gallu ymarferol, ond ydych chi'n angen gallu trwsio car. Mae yna lot o bobl sy'n just daio efo cyfrifiaduron. Ac i fi, dwi just yn mwynhau'r holl gwrs, a dwi'n mwynhau yr ochr bywyd go iawn a'r pethau da mae Peirianneg yn gallu gwneud i'r byd efo newid hinsawdd y falle. So ydych chi'n sbio rhywun sydd ddim yn sicr be maen nhw eisiau gwneud, a mae hynna'n ffain. Os ydych chi'n poeni, wel, ydych chi'n cael poeni, achos fi dylai fod yn poeni reit tron. Ond dwi'n gobeithio bod hwn wedi bod o fydd, fyswn ni hollol yn argymell i chi fynd a gwneud cwrs Peirianneg neu cwrs Ffiseg, so pob lwc i chi.